now is we want to look at how in several cases we do not necessarily have a good understanding of the application of linear regression. So let's take the example of this. We said that we can have multiple combinations of lines which can be used for separating. In that case, what we do is we actually look at defining one unique classifier by expanding the notion of a line to something like a margin. That's known as maximum margin. To that, we add the border points on all classes which actually touch that margin. And that's what is known as support vectors. So support vector machine is basically an approach where we try to remove the redundancy or possible multiple explanations if we take linear regression by removing that ambiguity and saying we have this one classifier which is this whole margin hyperplane plus the support vectors. So that is a very effective technique. Now, when we started talking about the support vector machine, let us look at a variant of the pattern we saw earlier, like this. Here, the point is, if we apply SVM directly like this, there's absolutely no way you can get a margin kind of an idea. On the other hand, if we take an approach where we say that we map the transformation from this plane to another plane, where we say that y equal to x square plus y square, z equal to y square plus x square. That becomes the new function which you're going to map. And then what happens is, if we call that z, if z is less than some value, they fall into one category. Z is greater than some value, it falls in another category. So this is one way by which you can extend this whole notion of SVM, basically, which is, I consider SVM as an extension of the linear classifier model. But what we can do is we can transform this notion of separation of classes by this margin plus support vectors to not only a linearly separable, but to other places where if you can create a resulting variable where you can get this separation. So if you take a z equal to x square plus y square, I'm sure here, because of this circle, all those within the circle will have z value less than the radius of that circle, but those greater than will have a different value. So there, in that revised variable, we will have an effective notion of a linear separation, right? In the sense, if we take our z to be a modified variable, which is x square plus y square, in that we will take something like a cutoff value which is separating the two classes in this case. I didn't want to delve into deeper into this, but this is one generic variation which people employ in mapping SVM technique to broader category of classification, so that we are not restricted to clearly linearly separable scenarios. And this trick is known as kernel trick. This is a very powerful trick, but think about it. There's not a clear mathematical form. It is something you have to look at the data, visualize it, understand, is there something where I can map the problem to a different dimension by creating a resultant z which I can use to clearly separate two classes. So SVM that way is a very powerful technique, and we need to understand that it is not necessary that we need to have a linear separable things. We can do it in places where you're able to clearly separate out by a transformation of the original data to a different plane. I'm not going to go detail of this, but that's effectively what it is. In this case, it was x squared plus y. You can think of other examples. Like I can think of if I take, say, a sinusoidal kind of a curve here, and we try to create something based on cube where we alternate between positive and negative. So that gives another transformation where you can say that positive versus negative classes for a transformed Z, which is based on cube. Like that, the key is for you to understand that you're using the same concept of separable classes separated by margin with support vectors, but you're talking about transforming the problem to a different variable.